There have been well over 3,500 earthquake aftershocks in Canterbury since the Darfield earthquake in September 2010. And no sign of them letting up yet, and Christchurch residents have become well used to being shaken around. And to help scientists understand the shaking better, some have been offering their homes and their home computers to create a network of tiny earthquake detectors across the city. Ruth Barron with GNS seismologist Anna Kaiser finding out more.
What have you got on the floor?
So we have one of these mini seismometers mounted firmly to the floor so that it will move as the ground moves and detect ground motions in 3 directions. So north, south, east, west, and up and down. Now this information is transmitted through a USB connection and collected on the host computer. So we have volunteers hosting these instruments.
So people in their own homes.
That's right.
There.
It uses your home internet connection to send the data back to a central server where it's collected, and we can use it for research.
Now there's lots of squiggly lines on the computer at the moment. Is that reading from that sensor, is it?
Sure, that is a display of what the sensor is currently recording. So at the moment, there are no strong ground movements. So
there's still lots of squiggles though.
Sure, this is background noise, if you like. There's always a level of background noise recorded at the sensor. When we have a strong ground movement, that will be stronger than what you see on the screen. So these are actually very, very tiny fluctuations.
Right. And where have you got these sensors at the moment?
So we have a number deployed in Christchurch following the Darfield earthquake, the magnitude 7.1.
The one that was in September?
September 2010. We deployed a number of these around Christchurch. We had up to 180 in the beginning, and now we have a smaller number that are recording. And these were to capture the aftershocks, or the ground motions from the aftershocks after the large event.
Right. And the one that hit in February, did you have sensors out for that?
We had a number of sensors out. We had about 30 actually out in Christchurch. We weren't able to retrieve records from all of those because of there were power cuts across the city. So
because the computer has to be on, does it, to record it?
It does. So the computer has to be on. It can collect the data and transmit that packet of data at a later stage. But if the computer loses power, then at that point we lose the data that would be recorded. Yes.
And are these some of these sensors here on the table?
Yeah,
they're
right.
really small, aren't they?
They're very tiny. They can fit in the palm of your hand, basically. They have inside them what's called a MEMS accelerometer, so it's similar to what you have in an airbag in a car. So if it detects a certain amount of acceleration, it can record this level or trigger a certain action.
And that's all sent to the computer, which then sends it to the host computer up here. Is that right?
Yeah, so the data is transmitted to the home computer, and then that's transmitted to a central server in 10-minute packets, if you like. So we have the whole database on a central server, actually located in California.
Right. Why in California?
So this project is actually part of a global network called the Quake Catcher Network. We're collaborating with our colleagues in Stanford University and USGS to do this project. They have certain other sensor arrays in different places. For example, they had a deployment after the Chile earthquake a few years ago. But in the Christchurch project, we've done something a little bit different. We've had a very, very dense deployment of these instruments, so in a really small scale within an urban area.
And what sort of results did you get back from the actual sensors that were on at the time of the February earthquake?
So we have, we record the waveforms quite quickly. We have an idea of what we call the peak ground acceleration, or the PGA, at the sensor station. So one of the first things we do is make maps of peak ground acceleration using also the GeoNet stations, the national network, but supplemented by these low-cost accelerometer stations. And then later down the track, we can also use the data to investigate variations in ground motion throughout the city. Our colleagues in California have also been using the network to test their rapid earthquake location algorithm, so they're looking to see how quickly they can get a quick estimate of the size and location of an earthquake within seconds or minutes of when it actually happens.
And is that the benefit of these? Because there are obviously seismograms out there, aren't there?
Sure. So we have a very good national network system run by GeoNet, and these have research-grade seismometers, which are obviously necessary for a lot of the research that we're doing. With this type of network, we can supplement that by collecting a great deal of data, so a large number of stations in a small area very quickly. So it's complementary, if you like. Part of what we're doing in Christchurch is also seeing exactly what we can do with these types of networks, because they're quite new, or quite a new thing in seismology.
And what did you find from the February earthquake? Do you actually have data from that?
Yeah, so we did record seismograms from the February earthquake, but what we've really been looking at overall is data from the whole aftershock sequence, so all of these smaller events that are going on. And what we can do, because we have such a dense network in Christchurch, what we've been doing is looking at the average ground response from a number of different earthquakes at a certain site. So when an earthquake happens, obviously there are lots of things that contribute to the ground motion that you might feel. For instance, the type of earthquake source you have, where it is, the size, the type, and the mechanism. Then also the path that the waves take from the source to your recording station will influence the ground motions. And thirdly, what we're really trying to isolate in this study is how does the local structure, or the local geology, if you like, affect those ground motions as the waves come close to the surface. So if we have a large number of recordings, we can effectively isolate this effect at different locations.
And what sort of things have you found about ground motion?
So what we really do is we look at how the ground motion varies with frequency. So different frequency waves will be amplified in different places, if you like, depending on the local geology. So, for instance, where you've got, say, a shallow soil with a narrow basin, you might see a lot of amplification of higher frequencies, so these will be coming in more strongly. Whereas if you're out on the plains, sometimes because you've got a deep layer of sediment, you'll be seeing a lower frequency effect. And sometimes, because in Christchurch you've got quite a complex shallow geology where obviously the rivers have come through and been deposited soils in quite a variable fashion, even around from place to place you might see different effects. So different frequencies are coming in more strongly than others, even on quite a small scale, even if you look at it, say, a couple of kilometres away.
So do you actually have data from the February earthquake?
We do have a number of accelerograms recorded from the February earthquake. Some of them are plotted here with the three components, so east, west, north, south, and up and down. And if we go through these, some of them, so for example, this particular recording was recorded a certain amount before the host computer lost power, whereas this recording
had it pretty much all over.
The computer kept power for the whole earthquake.
The up and down there is pretty full on, isn't it?
That's right. Actually, what we've been seeing in Christchurch in general is that during the February event, the north, south, and east, west components tend to be coming through with a lower frequency. You can see the wave peaks are spaced a bit further apart.
Yes.
Whereas the up and down motion contains a lot of high frequency energy, so you can see the peaks are very closely spaced together.
Yes. And the one below is just another aftershock, is it?
Yeah, so this is a smaller, I think this is a magnitude 5 that was recorded in October 2010. And so you can see for this particular event, because the ground motions are weaker, you can see the background level of noise is more obvious, if you like, is more apparent. But you can still see the earthquake motion that's coming through.
Yeah. And how does that feed back into telling you about ground motion?
So basically, with this particular project, you can see here on the left, you've got seismograms recorded at a reference station. It's a GeoNet research grade reference station, and it's located on rock, basically in the southern Port Hills. So you can see the ground motions here are quite small compared to this particular station. And here, this is one of our little mini-seismometers, and it's recording, or has recorded ground motion on the plains, basically, so a soil site. And you can see that the ground motions are stronger,
yeah,
compared to the station.
They've got more background noise.
Yes, and also what you can see straight away is that this low-cost sensor has more background noise. So the way we need to address that is to take a large number of these recordings over many events, basically, to really extract the proper signal that's characteristic of a certain station. And that's by taking it over a large number of data, you can reduce the influence of that background noise.
And what can this data be used for? Are people going to build better houses, do you think?
Well, ultimately, it's sort of a good way of getting a first idea about where the different variations in ground motion are occurring, what sort of frequencies are amplified in different places. And then we can go back and really look at the soil structure, see if we can find out exactly what's occurring there or why this is happening. And ultimately, the idea is that this feeds into engineering design. So engineers need to know what kind of ground motion will be experienced at a certain place, and this will feed into that sort of study. So not just, this will be telling you about the local site conditions, and then there'll be other factors as well that you'll need to consider in engineering design to mitigate the effects of strong ground motion.
Anna Kaiser from GNS.